Okay, thank you, Freddie. Yeah, hello, I'm Anna, and I'm going to present our work, a new concept for explaining graph neural networks. So our work is about explainability on graph neural networks, and we chose GNNs because many important real-world data sets are graphs or networks, like social networks, knowledge graphs, the World Wide Web, and many more. And while graph neural networks leverage link structure to encode information as well as incorporate node feature information and currently achieve state-of-the-art on many prediction tasks, they do lack transparency in their decision-making like many other connectionist models. And a number of subsymbolic approaches have been developed to provide insights into the GNN decision makings, mainly perturbation-based approaches, which then output a mask, edge mask, or feature masks with the most important or influential features. And while these are first important steps on the way to explainability, the generated explanations are often hard to understand for users that are not AI experts. So our approach targets experts of the application domain. Explainable AI and visits the widespread application of AI models should be more likely to succeed if the evaluation of these models is focused more on the needs of the user. And a common weakness among these subsymbolic approaches is the user's responsibility for compiling and comprehending the symbols in the final step, often relying on their own implicit form of knowledge and reasoning about them. And how the input, output, and the emitted symbols relate to each other is often an implicit cognitive intuition on the user side. So in this position paper, we address the weakness of those approaches or this specific weakness by proposing a post-processing rule-based companion to such a subsymbolic explainer method. And thereby we want to complement the subsymbolic instance level explanations with model level rules. So by extracting and aggregating global rule-based explanation through a standard white box machine learning method from the generated explainer subgraphs. By explainer subgraphs, I'm talking about these explainer masks that often visualize a smaller subgraph than the original input graph. We reduce the amount of additional interpretation needed by the user and provide a model level explanation that captures explanations about the global behavior of a model by investigating what input patterns can lead to a specific prediction. And as an example of such an approach, we developed a method we call subregs, where we take the output of the state-of-the-art explainer method as input, as well as graph-specific attributes, such as node distances and network motifs, and use decision trees as our white box model to generate rule-based explanations. And here you see the conceptual schema of this approach. And the goal is to generate systems that can provide model level rule-based explanations which don't rely on the user's understanding of the domain, where we try to achieve this by combining the results of a subsymbolic explainer method with a white box rule generator, which then should satisfy the representation needs for human comprehensibility and reasoning. And this rule-based explanation generation isn't a standalone approach, but an add-on post-processing method in order to enhance the explanations and make them more user-centric. So after training a graph neural network, you have an input graph, you train your graph neural network. The graph neural network's decision-making process is interpreted by identifying a sparse receptive field containing influential elements, so a mask. And our post-processing approach consists of taking these initial symbolic explanations and lifting them to the level of rules. So you can see here the process of generating a rule-based explanation for a node classification task, where we have an edge mask and a node feature mask that are generated by the subsymbolic explainer model, and then F, and then subsequently rules for edge and node features are created by the white box models D. And the rules are created through a classification process where the individual edges and features are assigned binary labels, influential or not influential, based on their masking value. And the white box model is trained using those binary masks as the target variable. The generated rules then function as a model level explanation for the respective classes of the original classification problem, and furthermore introduce a verbalization element that can make explanation more comprehensible for the user. An important part of generating a user-centric explanation is to make the explanation customizable and include provenance, for example, by including information about the domain knowledge utilized by the system to increase user understandability and also acceptability. Such domain knowledge can be included by extracting attributes from subgraphs depending on the domain and classification task. An example here of such inclusion of domain knowledge are graph-specific attributes, such as motifs, are mapped to the domain language. And in a more formalized setting, now here we are working with decision trees, but we've also started to work with more formalized semantic web techniques. Relational rules could also be included, for example, to represent domain-specific constraints. So to test this conceptual approach, we propose our subgraph models, which enables the generation of model level explanation. So here on the left side, you can see a input graph with a target node. So we are looking at node classification here, but could also be graph classification. And then we have the subsymbolic explainer, which identifies the important edges and features. And this information is then used as input for decision trees. So since the state-of-the-art method outperforms alternative baseline in explanation accuracy, we chose the GNN explainer as the subsymbolic method F. And as a method for extracting the rules, we use the standard machine learning mechanism decision trees. And then these decision trees can be linearized into decision rules. The classification by the decision tree is binary and based on whether the node is considered influential by the chosen subgraph, stemming from the edge mask, which is a 0, 1 valued vector, and therefore our target attribute for the white box model. And the attributes are extracted from node edge and graph meta information from the explanation subgraph. Since graph architecture offers more information than tabular data, it's vital to take graph-specific data, such as network motifs, into account. And in order to enhance the user-friendliness of our approach, the attributes are then personalized to the domain by mapping them to the respective domain terminology. The feature selection rules are generated analogously with the corresponding node feature mask. We used to try out our approach. We used the MUTAG dataset, which is comprised of molecule graphs labeled according to the mutagenic effect. And there we carried out graph classification with a vanilla graph convolutional network. And in the next step, we generated edge masks and node feature masks with the GNN explainer, and then applied the decision trees. So here you can see some first results. So These are model-based, model-level explanations. So, for example, in terms of features, in terms of molecules that are mutagen, or explanation would, for example, look like if molecule contains atom C and atom O, or for the edge rules, if atom has more than 2 bonds and if atom is part of an atom ring. So the exacted node rules gives the user a comprehensible idea of the network motives that are influential in the GNN's decision making, either being part of a cycle motive, so for example, an atom ring, or with a high degree, so more than 2 bonds, or not being part of a cycle motive and having only 1 bond. Also, the node feature rules represent clear explanations which atoms, for example, atom H, are influential in their respective classification. So we can see that subgrex correctly identifies that atom N and atom H are not being in the molecule is influential for classifying it as non-mutagen, which is the chemical group asanid, which is known to be mutagenic. No-node selection rules with a low Gini impurity could be extracted for the non-mutagen category. That's also interesting, as it indicates that no feature is influential enough to generate a model-level explanation of when a molecule is classified as non-mutagen. And we report the sensitivity to show to which extent our explanation can function as a model level explanation. Sensitivity here indicating the ability of the decision tree to correctly classify a node or a feature as influential. Sensitivity lying here between 72 for mutagen node selection rules and 98 for mutagen feature selection rules, and therefore indicating a high level of model explainability.
And now you have 3 more minutes to go.
3 more minutes, okay. So, we have proposed this conceptual vision for how to approach generating more user-centric rule-based explanation from sub-symbolic instance level explanation to improve model level understanding. And our initial experiments show that even with this very simple subgrex model method where we use decision trees, we do get some surprisingly effective results in terms of meaningfulness of the explanations, and with a high sensitivity, so high capability to explain, to have a model level explanation. In further research we're working on, though, we're using semantic web technologies, where we use inductive logic learning to allow for deeper integration with background knowledge through the use of domain ontologies, so that we have a much more structured background knowledge base, which to use as a resource, and also to create instance level explanations for the individual predictions. And also then being able to calculate the fidelity for our explanation from the student model, so the inductive logic learning, and towards the teacher model being the graph neural network. And furthermore, the advantage of then including semantic web technologies would be that it comes with reasoning capabilities. Yeah, that's all from my side. Here the references, and thanks for your attention.